Welcome everyone. This video is going to be covering the finer details, the tolerances, different positions and so on for my magnetic track. Before we get into those details, I want to say thank you to YouTuber Motion Magnetics for reviewing this track. I designed this a long time ago, like 20 years ago, and thought it was never really going to get much attention, and luckily he decided to review it, and big thank you to him. So I placed a level here, a spirit level, so we can see. I'll try and zoom in without affecting it too much. We can see that it's level, but if anything, a small uphill incline. That bubble could move maybe 1 mil to the right to be perfect, and I thought I would leave it in that position just so that you can see that it's definitely not a downhill run, it's an uphill run, but that doesn't really matter too much to this system. So we've got 3 magnets in center of screen, and on the opposing side there's the other 3 magnets. The elevation could be slightly different, but I wanted this perspective just to start off with, and I'll take different shots from different angles so you can get a real understanding of how this system operates. For this one, I wanted it on this side profile so that we can see at which point, if we use this 3D printed nut here as an indicator, and so here we're on the edge of this last positioning for another set of magnets to go in place, and this is pretty much the spot of where it can go either way. It can either roll back away from the system or roll into the system, so it's pretty much on top of the hill, and from what I can gather, it's around about the 15 millimeter or so. The full gap here is 15 millimeters, so that looks like it might be sitting around about the 10 mil mark, where it's neither repelled nor attracted. So for starting the system, mid-track, for example, which I will demonstrate in this video, that positioning is critical, and that's what determines this gap here in the first place. It's so that it's a sufficient gap to overcome the next set of magnets, to allow that inertia to have its effect on that system. So if we were to give that a tiny tap, we could roll it over that hill. Now from that position, it will leave that set of magnets. Say we tried to start it within, it tries to get away, but it can't actually do that, and that's why the further you go towards the starting position, it's like the further uphill you're taking this, so you get the ability to run away from this magnetic field if the hill, if the roller starts high enough up the hill, or in other words, far enough back into this field that it's getting the full effect of the field. So we go right on the edge there, where it's a case of me not tapping it to supply, but just allowing it to do its own thing. So we find that sweet spot, and then we can let it go rather than pushing it, and it will always in my experience with these dimensions, it will always move away from that. So now what I'll do is I will position another 3 magnets and reposition camera and check the spirit level again, and we'll show the regauging of a secondary set. So here we have a secondary set in place now of 6 magnets with both sides, but we're keeping this horizontal perspective just so that we can be sure of the starting positions. Once again, it checks out to be level. So now if we place the roller in this same position, we now know that the top of the hill, so to speak, for the magnetic flux is around about the 10 millimeter mark from the first magnet. So if we position that there, so it wants to roll into the field, now we've got a large enough gap here, the distance of another set of magnets. So 1, 2 and 3 would be positioned there, and even though that's a significant gap, if the roller is started from the correct positioning, then it will clear that gap and it will negotiate the second set of magnets. So we'll demonstrate that now. We'll get that on on the crest of that hill, so we can get it to go in either direction, and we'll let it go. And it clearly, you can see it clearly slows down. It attempts to stop with the resistance from the secondary set of magnets. However, its own inertia through the acceleration of its own mass is what allows it to break that 1 inch barrier that Motion Magnetics talks about in one of his videos. I mean, admittedly this is longer than 1 inch, but he's absolutely correct in that instance that when I initially applied a similar system to this in a rotary form, it pretty much cancels out all of the individual magnetic fields and turns an existing track into instead of having separations, it becomes one solid track. So magnetic flux is then distorted. For example, when I created my first rotary system and placed it on a CRT old school monitor or TV, I could see the field no longer resided with each individual magnet, but became so a northern and a southern hemisphere. So it completely destroyed the lines of force that I had imagined. So now we've got the understanding of where the starting point is. So you can imagine now a track being broken up in this way so that you can prevent that individual lockup, and that's the reason for the spacing of 5 mil, 10 mil, and then 15 before the next magnet, is to have a difference in potential. So this at the start of the track, and each set of 3, it's the same relationship. At the start of the track, the force field is intense, and as the roller moves through, its inclination for it to go backwards is less because there's higher resistance. These two magnets are closer to one another, and so the resistance going this direction is higher, and it has a tendency to overcome this locking barrier by using its own momentum created through inertia due to its own mass being moved. It's just harder to stop. So you can see there it will resist, it will slow down, but if the spacing is correct and adequate, then it will still re-gauge and re-enter and leave the track. It'll leave the secondary track without any hesitation, and so this process can then be repeated. You know, if you change that structure, which is what I will do in a second, what I'll do is we'll place 2 tracks together, and then we'll have a gap, and then another track, and then another 2 sets of tracks together, so that we can show that even if we have unequal forces, so we've got 2 sets here, then followed by 1 gap, then 1 set, and 1 gap, then another 2 sets, you can see that you've got a large stator versus a small stator, and then back to a large stator. So we will be able to see that even that won't stop this. Now I can start this from any position within the track where I don't actually have to apply any more energy than it takes for me to let go of the roller. So as long as it's placed in the correct position, trying to start it at the end of any individual track is not going to work. And that's why it's so important that we acknowledge this separation of spacing and the increase in increments that has this roller wanting to roll you know, to the lower amount of resistance, to put it basically. This magnet is further from this magnet, and therefore there's less resistance going in this direction. So that's pretty straightforward. So we can now establish, with that repeated configuration, we can now start this wherever we want. So what I might do next is place place a gap, so a set of 3, then a gap, then a set of 3, then a gap, then a set of 3, and we'll record it going through multiple stages. Okay, so this is a slightly different perspective. We'll check it with the spirit level again, and it still has that tiny uphill run. I haven't actually moved the track, I've just placed new magnets in. So now we've got 1, 2, 3 sets here, and then the beginning of a 4th set, and I just need to grab more magnets to make that a full set, but that won't cause any hindrance. That will still allow this to roll. So if we take the roller and position that right at the beginning, you'll then see there's that tiny bit of resistance for each set, but due to inertia it can overcome that, so that's not going to be a problem. And this is why I say to you that you can run this for as long as the track runs, unless there's, you know, outside interference, like, you know, a big gust of wind blowing the opposite direction. You know, nothing runs forever. There is no such thing as perpetual motion. Even a device that would be 100% efficient would still require maintenance, which means you would turn the thing off, and therefore you've lost your perpetual feature. So there is no such thing. Let's, before anybody jumps on the comments, oh, you realize this won't run forever. Yeah, I realize nothing runs forever, not even the sun. So now that we got that out the way, we can see that there is resistance between each set. I've designed this to fill all positions along this track. So you know, it can even overcome that reduction in inertia by that big gap that's there, and still re-enter the next phase, which is one of the things that they always said couldn't be done. I'm not suggesting that you loop this in a constant track because of this re-gauging thing. If this spacing was to be ignored and you were to use your own spacing, and this is not suggesting that other orientations will not work, but in this one, if there isn't this inequality, the system doesn't work. It does have no reason to move in any direction if all forces are equal on opposite sides. So there is just no point. In my experience, systems that are equal do not work. That's my experience. Someone else can come up with their experience if it's been different to that, and explain to us how that works. But for me, I can't do that. This is what I can explain because I know this system works. So can we start it from any position in the track, which has been one of the major questions. I was like, oh, you can't do that. So it can, and we can see there that even though that resistance is still there, it can still overcome that. So we'll get that on that peak where it wants to go either way. We'll let it fall the way it's designed to go. And even though it almost comes to a stop, I'm not applying input power. I'm letting this thing go at the top of the hill. I'm not even pushing it off the hill. I'm just releasing it, and it almost comes to a stop, but its inertia is what allows it to get through to the next position. So in forming a rotary version, that part of the equation, in my opinion, must be respected, must be honored. Without inertia, and therefore without the correct mass, and it's a relationship between your magnets. At the end of this video, we'll have photos of the inside of this rotor, and I've done that to show the sizing of the magnet, the spacing from the tops of these magnets to the bottom of the rotor is important as well. If they're really close to these drive magnets or stator magnets, then there is too much violent opposition, and it's the same with Professor Searle or John Searle's levitation disc or magnetic motor, whatever you want to call that. He has the same a certain requirement of rings that go on the external perimeter of the rotor magnets, or sorry, stator magnets, and that's because if you place them directly on surface to surface, it's way too violent, and out at that edge, so this far from those magnets, there is a different field, and it almost comes into a point. So you're riding on the crest of the wave. It's like, imagine trying to start your surfing ride at the bottom of the wave. It's not really, your power is coming from the top of the wave, in my opinion. You've got gravity you're requesting that you return to the base. You're returning to the lowest point, and that is pulling you down the face of the wave. I believe that's what's happening with this instance here as well. So we can see there that I've got that the wrong way around now. We can see there that you can start it at that sweet spot on top of the hill. It will roll segment after segment, it will declare, or it'll arrange its set speed based on the parameters of the magnets. Alright, so now we'll go to full sets. So what we'll do now is we'll have 2 sets of magnets, then 1, and then 2, just to show you that it can go through those different orientations as well. So we've shown there it can actually be started mid-track, and even though there's less inertia, it's still capable of leaving subsequent tracks, just as long as your starting position is taking the most advantage of that inertia factor. Now we have 2 sets at the start here, a gap equal to 1 set, 1 set in the middle, another gap equal to 1 set, and then we've got 2 sets to finish off the end of it. I'll demonstrate that we're still level or on the uphill climb. So just to make anyone happy who's concerned that it might be a downhill run, that is clearly not the case. It's an uphill run. So working against the design and not trying to help it anyway. So now if we start again in that same position right at the start of the track, just at the point where it wants to fall in, and it'll pass through the first 2. And you can see there with this, now this is not an ideal configuration. You should have stator assemblies to be similar. In essence, this is big hill, small hill, big hill. One would naturally assume that coming off of a big hill, we can easily run off and up and over a small hill. But then coming off of a small hill to run over a big hill, that wouldn't normally be a reality, in my opinion. I could be wrong. I'm willing to be wrong. So if we place that at the start position, we can see it almost tries to stop because of this inappropriate configuration. But the inertia still has the ability to overcome that. Again, I don't apply any force here. I apply the initial force to carry the rotor to its starting position, and then I let it go. Now, one would assume if we're only going to use the power of this little hill, that we can't make it up over the next bigger hill. There's just not enough inertia, not enough of a hill to overcome the subsequent larger hill. So we'll find that sweet spot, and we can see there that we're locked. So that's why I wouldn't use that configuration. I wouldn't use 2 sets, a gap, 1 set, a gap, 2 sets, because you're going, you need to use each individual hill, and the inertia and mass of the roller must overcome each hill. Whilst that can be a reality in this configuration, if starting from the big hill, it clearly struggles if you start from the little hill. Alright, so that's been demonstrated. I will now move on to having a solid and complete track. And in saying that, it's still sets of 3s, so it's individual tracks of 3s. They're not to be considered as as one track, and this is why I'm comfortable believing that it will continue for the full length of the track, because I know that it's not seeing them as a full track, it's seeing them as individual separate tracks, which it is quite clearly capable of negating the resistance. So next assembly. Okay, so for this one, this is all of the magnets in a consecutive line, and all in their sets of threes. All the gaps or spaces are being used. Spirit level to show that it's still level, so we're not cheating. We're still doing an uphill run, so I could make it level, but I think an uphill run gives my theory an advantage, because you can see that not only am I not using the downhill run to my advantage, I'm going against the advantage. So now when all these magnets are all in their spaces without any large gaps, it changes the magnetic configuration again. So this tolerance for being able to start anywhere in the track, it still exists, but you do need to move closer to the first magnet of each set, rather than in this initial position. We're way out here at around about the 10 mil mark, having the 3D printed nut in that position, and the position where it wants to fall in becomes smaller and smaller based on the length of the track. So now we're starting to get into that the fields are actually changing to represent the entire track, but they haven't changed so much so that they can't still perform their individual function. So now the starting position is a lot closer to the first magnet. And if you look in at this middle of the video, you'll see that it was around about this position, around about 10 mils from the start magnet. But now in this case that we've got a much stronger field to play with, it's almost right on the edge of that magnet. So now if we allow that just to fall in, we can see that it will resume and pick up speed in an attempt to be self-regulating based on its inertia, its propulsion. It will come up to speed and it will self-regulate that speed. Again, that's purely based on the array. So can we now start from somewhere inside the track? Yeah, we can, but the further we go in, the more we have to consider slightly adjusting our starting position. So at the start of the track, it's right on the edge. At this point of the track, we're still receiving resistance from the repulsion from the start of the track. So it changes it again drastically. So if we were to start it there, you can see that it literally will find a way to get up to its speed. And the longer the track goes on, the faster it will get until it reaches top speed, which is again governed by the arrangement of the magnets. You change spacing of these magnets, you change that arrangement, therefore you change the governing speed, self-governing speed. So I can start that just about anywhere in that track, as long as I keep in mind that I've got to find the top of the hill for each individual set of 3 magnets. So that looks like the neutral zone there. If I walk it a tiny bit this way, it will try to fall again. And see, that new falling spot is different. And so it's a case of finding that sweet spot each time. And you know, I literally have spent hours doing just that, just moving it a couple of mil in one direction to find where is the new position. And it's always a difficult thing because you can't see the actual flux lines. See, you don't really know. I mean, I could just apply force here and put input into the system, but that's not how this system works. You've got to find that sweet spot. There's not quite it. And we just got to keep moving it until we can find it. And you're not applying force is not really that realistic. I mean, every motor is going to receive a startup pulse. But the most important feature is whether this thing can be started and leave the track, and that was always the thing that I had difficulty with most arrangements, is that we couldn't leave the track, whereas this one is more than capable of doing so. If you've got any suggestions, any recommendations, if you can, you know, purchase your own magnets and do some research. I will put the 3D print files up on the internet, also on my YouTube, on this video, in the description. So please, you know, put constructive criticism towards this. You know, I know what it can't do. I want people to help me get it to that next phase. I believe together we can all have this achieved and have any remaining bugs ironed out, so to speak. I feel I've done, you know, 95% of the work. There are some things that are still yet to be realized, and we won't have those until we start getting into the rotational version. All right, thanks very much for watching. Again, big thank you to Motion Magnetics. Please like, share, subscribe. Please add your comments. I'm really interested to see just the variations that come from other minds. Sometimes you can get a little bit stagnate. You're with your own ideas constantly mulling over, whereas that input from someone else could be the difference. So thanks again, have a nice day.